into R, which is bounded. And then we had what is known as a partition P of the interval AB. The first one x0, x1, xn minus 1, xn, the last point, which is nothing but the point B itself. Right. Well, here what is that is to be observed? X0 less than, so there is a strict order. Right, so this is what we have. And then we defined two quantities. One is UPF summation 1 to n capital Mi into xi minus 1. Right, so what is this capital? Yes, any questions? This capital Mi, it's nothing but the supremum of the function. Because the function is bounded in the whole interval, it is also going to be bounded in the interval xi minus 1 to xi, and therefore supremum makes sense. In the interval xi minus 1 to xi, f of t, right? And similarly, we defined what is known as LPF, which is summation 1 to n small mi into xi minus 1, right? Wherein small mi is the infimum over t in xi minus 1 xi f of t, right? So some simple observations that we had. First one is that LPF is always less than or equal to UPF for any partition. P. This is first thing. Second thing that we had is what is known as if P and Q are any two partitions, of the interval AB, such that Q is a refinement of P. That means what? That means this P is contained in Q. This P is contained in Q. Yes, which means you are adding more points to the existing partition. Then the lower sum this is increasing with respect to the refinements, and the upper sum is decreasing with respect to the refinements. Yes. Fine. Yeah, these are the two things that we saw. So yeah, so this sum.
Sir, is this containment, I mean, Q is the refinement of P. Is this strictly contained? I mean, proper containment.
When you say refinement, so what is the point in taking equality? There is no point in taking equality.
Okay, okay. Thank you, sir.
Right, so this first sum is what is known as upper sum, and the second one is what is known as the lower sum. Right. Having observed these two, there is one more simple. Maybe let me put it in the form of lemma, or I think I still have it as, yes. Right. Well, so yet another observation. In fact, if yeah, so the first observation is that the lower sum is always less than or equal to the upper sum, right? So if P and Q are any two partitions, then the lower sum with respect to one partition is always less than or equal to the upper sum with respect to the other partition. Sorry, I don't need this P again. Here it is Q. There is no relation between P and Q. P and Q can be any two partitions. It doesn't matter which one you choose. Yes, so let's go for a proof of this. The proof is quite easy. So what we are going to do is, so first, yeah, so note that P union Q is a partition. If you take the union of two partitions, it is again a partition. Thus that it refines both P and Q. Yes, not only that it's a partition, it refines both P and Q. Yes. Therefore, LPF increases, lower sum increase with respect to the partition. Therefore, this is less than or equal to L P union Q with respect to F. And for any partition, lower sum is always less than or equal to the upper sum UP union Q. And upper sums, they always decrease with respect to refinements. And that's it done. Yes. Right. So what is that is observed? The lower sums, they always increase with respect to the refinements, and upper sums, they decrease with respect to, right? So we are going to use this idea. So having observed this, so let me define integral a to b. Well, there is a bar. At the bottom, there is a bar. F. So some people write it as fx dx or integral a to b f with a bar in between. Sorry, with a bar below the integral. Yeah. So this is defined as the supremum over all partitions of the interval AB, supremum of all lower sums, and the supremum is taken with respect to all partitions. So this is what is known as the lower integral. And similarly, the other one, integral a to b, and there is a bar above the integral f, which is defined as the other way, infimum over all partitions, upper sum. So infimum of all the upper sums, where the infimum is taken over all partitions. And this is what is known as the upper integral. Right. And because of the last observation that we made, that for any two partitions P and Q, lower sum is always less than or equal to the upper sum, it follows that, yeah, so maybe, yeah, so, well, again, yet another simple observation is that the lower integral is always less than or equal to the upper integral. Yes, so this is one of the simple observations that you can always make. Right. Okay, so let's, now here is the definition. We say that a function f, well, of course, it is always defined on the interval AB. F is Riemann integrable if upper integral is equal to the lower integral. Yes, if lower integral and upper integral, if they both are one and the same, then we say that the function is Riemann integrable. Right. Yeah. So because based on this remark, whatever observation that we made, the previous just before that, so in order to show that a function f is, so many times I write only Ri, so please understand that it is Riemann integrable. Yeah, and sometimes I write only Fn, which means function. So that doesn't mean that these are all the standard shortcuts. No. Only to save time, I am writing all these. Yes, function f is Riemann integrable if, so in order to show that the function f is Riemann integrable, it is enough to show that the upper sum is less than or equal to the lower sum. Because we always know this, the other one is always known to us. That the lower integral is always less than or equal to the upper integral. Therefore, to show that a function is Riemann integrable, it's enough if you can show that the upper integral is less than or equal to the lower integral. Right. Now let's do some simple examples. First one, f from 0, 1 to r, given by fx equal to x. So let's choose the partition Pn. In this case, let's choose it as 0, 1 by n, 2 by n, n minus 1 upon n, till the last one is n by n, which is 1. Yes. Yes, please calculate UPNF as well as LPNF. Start. Yeah, so I want each one of you to work out the details. Please start the details, working out the details. Please start. I am not going to work out these details. It is only you who is going to work out the details. Yes, what is the supremum in the interval I minus 1 upon n to I by I upon n? What is the supremum of the function fx equal to x?
Sir, I upon n.
I by n.
Exactly right. It's only I upon n, and the infimum
I minus 1 upon n.
I minus 1 upon n.
exactly I minus 1 upon n. Right. So you all have come to the level of MSc, and therefore a minimum set of calculations is expected from your level. You all are supposed to work at this stage. Not that I write everything on the pad or board so that you can easily copy it and go. No. It's the right time that you all will have to work. If you have finished the calculations, just raise your hand. There is an option for raising your hand. Please raise your hand if you have finished it. If you are finding it difficult to do the calculations, please inform us. Please inform, unmute yourself, and then inform that you are not able to do the calculation. Yes, others. I'm sure that it shouldn't take much time. What you are supposed to know is only the formula for what? Sum of
Nth. First n natural number.
Exactly, that's it, done. 1 plus 2 plus 3 plus up to n. You should, if you know the formula, then you should be able to. Yes, others. When will you finish it? Right. Yes, Mahesh. What
Yes,
is
sir.
the upper sum?
Upper sum is going to 1 by 2.
No, what is the upper sum? Value of this U of PNF. UPNF.
Just a minute, sir. Just a minute. Summation n square is going to that 1 by n square plus 1 by n into 1 by 2. Okay.
Yes, Prashant. Prashant.
Hello,
What
So
is the upper sum?
okay.
n plus 1 upon 2n.
Exactly. Very good. Good. Yes, Yash.
Sir, n
Yes.
plus 1 upon 2n.
Huh?
N plus 1
Lower
upon
sum.
2n. Oh,
First
lower
one.
sum, n
Yes,
minus
lower
1 upon 2n.
N
N
minus 1.
minus 1.
Right. So now you can easily notice that the first one and both the thing, they both converge to half. Yes. So what does it tell us? The upper sum, they converge to half, and lower sum, they converge to half. So what does it tell us? So it tells us that the upper integral is less than or equal to half, while the lower integral is bigger than or equal to half. That's what it says. And therefore, So this implies that f is Riemann integrable. Right. Is this clear? Yes, please lower your hands. Lower your hands. Yes, now let's do the next one. Second. F from 0, 1 to R given by fx equal to x squared. Yes, so choose the same partition. Yes, please start. You don't have to wait for me. Same partition 0, 1 by n, 2 by n, same thing. Calculate UPNF, LPNF. If you are finished, raise your hand. Yes, others. Yes, this example takes few more seconds. I don't deny, but still, having come to the level of MSc, you should be able to. This is not a difficult example. So it looks like the same set of 21 students have raised their hands. What happened to others? Why not? You all work. Others. Yes, Prerna.
Yes, sir.
What is the upper sum?
1 by n square, n plus 1, sorry, sir, n plus 1, 2n plus 1 by 6n square.
N plus 1, 2n plus 1 upon?
By 6n square.
Right, good. Who else do I have? Yes, Nirmal.
Yes, sir.
Lower sum.
N minus 1 to n minus 1 by 6 n square.
Very good. Yes. Yes. So now please lower your hands. And you can notice that they again both converge to 1 by 3. Yes. And as usual, yeah, I'll simply say that, show that f is Riemann integrable. Right. Right. So I'll simply put this within brackets. Fine. Yes. So one more example. So let me choose b to be something bigger than 1, and then you consider the function f from 1 comma b to r given by fx equal to 1 upon x. Now, well, what will be the choice of the partition? Here it is something different. For each n, and then choose r in r such that r raised to the power n is b. Right? So you have this. So now choose the partition Pn in this case as 1 r raised to the power 1 by n, r raised to the power 2 by n, up to r raised to the power n minus 1 upon n, and r raised to the power n, which is exactly b. Yes. Yes. Now calculate. Yeah.
Sir,
So,
sir,
ah,
r
yes.
raised to power n by n is coming out to be r now. Here it should be r square, r cube.
Right. Thank you. Sorry. Right. So it is r square, r cube, r power n minus 1, and r power n is b. Right. Thank you. So, yeah. So you can notice that the lower sum in this case I have calculated, which is going to be b raised to the power 1 by n minus 1 upon well, there is an n here, and then b raised to the power 1 by n, and then the upper sum, which is going to be n into b raised to the power 1 by n minus 1. Yes. And yeah, so you can also show that they both converge to log b. So all these I am leaving it as an exercise. Yes, so which you all should be able to calculate. And therefore it is Riemann integrable. Fine. Yeah, so well, we have been looking at examples which are only Riemann integrable, and the two nice functions with some nice partitions. Let's at least look at some weird example. Otherwise, if all the functions are Riemann integrable, then there is no point in doing this course. 0, 1 to r given by fx is, yeah, so this is one of the standard examples in analysis. In many places, this example is going to help you. Many places. One, if x is rational, 0 if x is irrational. Right. Yes. Yes. So now for any partition, choose any partition P of the interval 0, 1. Tell me what is LPF and UPF. This should not be difficult. Yes. What is LPF and what is UPF for this function? 1 if x is rational.
0 and 1.
Yes, so the lower sum is always 0 and the upper sum is always 1. So I'll simply leave it as an exercise. Again. Yeah, this is not a difficult example, but you should be able to observe. That's the whole point. Right. So what does it tell us? What does this example tell us? That is very important. So this is true for every partition. Therefore, what does it tell us?
Not integrable.
Exactly. Yes, Manoj Kumar. Manoj? You have raised your hand. Yes, what do you want? Do you want to ask something?
क्वेश्चन 2 में किया था.
अच्छा ठीक है, fine. Fine. So, well, why is it not Riemann integrable?
Hello. Sir, I think UPF should be B minus 1. Oh, okay. Sorry.
So why is it not Riemann integrable?
Because the lower sum is never going to be equal to upper sum for any partition.
For any partition, upper sum is always 1 and the lower sum is always 0, no doubt, whatever it may be. Whatever be the partition, it is independent. Therefore, the infimum of all the lower sums is, supremum of all the lower sums is 0 and the infimum of all the upper sums is only 1. And therefore, lower integral is always 0. Lower integral, in this case it is 0 and the upper integral is 1. Why always? Right? And therefore, it is not Riemann integrable. Fine. So, I don't want to repeat the arguments again. So, let me just say that, show that f is Riemann integrable. F is not Riemann integrable. Right. Fine. Yeah, so having done lots of examples and all those things, how long will we, so given an arbitrary function, how long are we going to find the partition, blah, blah, blah. Here in these cases, it was easy because there was a nice partition which helped us. But for an arbitrary function, how to know whether it is Riemann integrable or not? So we need some other method or some characterization which will help us to calculate. So let's work out. So here is a characterization which I'll put it in the form of a theorem. A bounded function f from AB to R is Riemann integrable if and only if for every epsilon greater than 0, there exists a partition P epsilon such that UP epsilon F minus LP epsilon F is less than epsilon. So if we can show this one, then we are done. Fine. So this is going to, we'll also see how this is going to be useful. Fine. Proof. The proof is not a difficult one. Forward part. Suppose that f is Riemann integrable. Yes. So what does it mean? That means that the lower integral is equal to the upper integral. Fine. This is what we have from the definition. Well, now let's start with a epsilon positive. Fine. Now once you have an epsilon, now how did we define this lower integral? It's the supremum over all the partitions. So once if I subtract something from the supremum, that is not going to be the supremum, right? Then there exist partitions P1 and P2 such that so this lower integral, it's the supremum of all the over all the lower sums. So you will get LP1F is less than, sorry, it is bigger than the lower integral minus epsilon by 2. Yes. And yeah, for the upper sum, it's the upper integral, it's the infimum. So you will get the other way. This is less than integral a to b, in fact the upper integral plus epsilon by 2. Yes. This is just from the definition of infimum and supremum. So now what we are going to do is that we are going to refine, sorry, here you need 2 because we do not know whether we get the same partition or not. So yes, so let's use it as 2. So now the partition that we wanted is the following. So let P epsilon equal to P1 union P2. That's it. So we have chosen the partition. We'll have to only verify that this is the partition that we are interested. So then, yes. So now what we wanted is UP epsilon F minus LP epsilon F. Right. Now we are going to make use of the 3 observations that we made in the beginning. Yes. P epsilon, this refines both P1 and P2, and upper sums, they decrease with respect to the refinement. Therefore, this is less than or equal to UP1, sorry, P2, because that's what we have. And lower sums, they increase with respect to the partitions, but because we have a minus, so this is minus LP1 F. And then now let's use whatever we have written above. Yes, so this is going to be less than the upper integral F plus epsilon by 2. And then you have minus of this. And therefore, if I choose a minus, I'll simply have minus integral, the lower integral plus epsilon by 2. Yes, that's it. But the first straight line says that these two are upper integral is equal to the lower integral, and therefore these two integrals, they get cancelled, and what you're left with is only just epsilon. That's it, done. Fine. Yes. Fine. Now for the converse. Yes, so now let's do the converse. So let epsilon greater than 0. Then by assumption, there exists a partition P epsilon such that UP epsilon F minus LP epsilon F. This is less than epsilon, right? So now what are we supposed to show? We are supposed to show that F is Riemann integrable. And in order to show this, the only thing that we have is the definition. And from the definition, what is that we'll have to show? We'll have to show that what are we supposed to show? Upper integral is less than or equal to the lower integral. Yes. Upper integral is less than or equal to the lower integral. So how to show that A is less than or equal to B? There is a way to do this. This you must have seen even in real analysis. To show that A is less than or equal to 0, B, it is enough to show that A is less than B plus epsilon for every epsilon positive. If we can show this, that A less than B plus epsilon for every epsilon positive, then we are done. That should imply that A less than or equal to B. Right? So if you have not seen, then let me just give a simple exercise. Right. So here is an exercise that let A comma B belong to R. If for every epsilon positive A less than B plus epsilon, then show that A less than or equal to B. Yes, so this is the exercise. Yes, so when you come for the next class, please be prepared with the proof of this. I may ask anyone from the class, so please, fine. Now we are going to use this one. So what are we supposed to show? We are supposed to show that A less than B plus epsilon. So we have already started with an epsilon positive, right? So not that we did it because it is an assumption. We did this because of this one, right? So this is our idea, right? So what are we? So our claim is that upper integral minus the lower integral is less than epsilon. If we can show this, which is equivalent to saying what we wanted, A less than B plus epsilon, which is equivalent. That's exactly what we wanted, and we are going to do this, right? Yes. Right. Fine. Now, upper sum minus the lower sum is less than epsilon. Well, what is the relation between upper sum and the upper integral? Yes, Manoj. You have raised your hand again. Fine. If you are not responding, then fine. Well, what is the relation between upper sum and upper integral?
So upper sum, infimum of upper sum is the upper integral.
So infimum of all the upper sums is the upper integral. Therefore, upper integral is always less than or equal to any specific upper sum. And similarly, lower sum This is always less than or equal to the lower integral. Yeah, so fine. So observe that the upper integral is less than or equal to upper integral, upper integral is always less than or equal to the, it's always bigger than, upper integral, it's the less than or equal to UP for any partition, UPF, and because this is defined as the infimum, and the lower integral is always bigger than or equal to the LPF for any partition. So in particular, what is that we have? Integral a to b f. This is less than or equal to UP epsilon f, and yes, this is bigger than or equal to the LP epsilon f, right? Therefore, we wanted the difference, upper integral minus the lower integral. Yes, so upper integral is less than or equal to the upper sum corresponding to this partition, right? And the lower integral is bigger than or equal to, but because you have a negative sign, this is minus LP epsilon f, and the difference as per our assumption is less than epsilon, and that's what we wanted. And we are done, right? Yes, so let me stop here. Yeah, so I want your comments in a few within, I don't have much time. I'm already exceeding the time, so please, I want your comments. So please tell me whether I'm going fast or slow. If you feel that I'm slow, let me increase my speed. So that, because I'll have to do a lot. Yes, please. Anyone? If I am fast, please tell me so that I can also lower my speed. Let me try to reduce the speed as much as I can.
Currently fine, sir.
Okay, good.
Fair, sir.
Huh?
Fine, sir. Fair.
Oh, fine, good.
सर ठीक है सर.
Okay, ठीक है. Fine. So let me stop the recording.